Okay, dude, we are live. I'm going to reach over. Dan is looking up on his phone. So, like 30 seconds ago, I said, now, wait a minute, don't prop it up like you know it. Dan is propping up the phone. We're really bad at telling when our other classes were. And I said, okay, I'm gonna go live now. And Dan said, wait, I gotta look up when our longitudinal SEM class is. Because
do you know when it is?
It's this spring.
It's this spring. Do you know if it's May or June?
Spring is until June 21st. So it's
true.
It's this spring. It doesn't matter. Welcome, everybody. It's just really funny. It's like, I'm going live, Dan. And he's like, wait, as he's getting his phone. Yep, we are nothing if not prepared here.
Well, the last two times we failed to remember when things were.
Yes. So welcome. I'm Patrick Curran. This is Dan Bauer. We are at the University of North Carolina at Chapel Hill. We also run CenterStat, where we offer classes at times that neither one of us is aware of.
Could be May, could be June.
Could be May, could be June.
Next December.
We have some in December. I remember that. So thank you so much for joining us. All right, episode 1. We talked about structural equation modeling. Episode 2, we talked about multi-level modeling. All right, now a side call out is I said that with total confidence. Right before we went live, I asked Dan what our first 2 episodes were. So
you get to a certain age. Do you remember what we're doing today?
It involves a blue pen. That's all I know. I did learn, so we also try to provide professional development tips. And one is, as you age, quit saying it's nice to meet you. Because about half the people will say, well, you were actually on my dissertation committee. And so don't say it is nice to meet you, say it's nice to see you. See? That way they have no idea when you say, buddy boy, guy, hey, you, which I occasionally do to you. Okay, what we're going to talk about today is the structural equation modeling based latent curve model. All right, so a handful of people are watching live. Chime in, where are you? Oh, somebody posted June 12th to the 16th. Thank you for knowing more about our scheduling than we do. Longitudinal SEM is June 12th to the 16th. So what we're going to do, it's kind of fun. This is the beauty of being in academia. Is pretty much everything we taught you in episode 1 and episode 2 are fundamentally wrong, I would say, in the sense that we fit very complicated models to cross-sectional data. And in each of the episodes, we talked a little bit about within-person effects, between-person effects, within group effects, between group effects. And if we're studying the individual, and this can scale up and down, you fit growth models to mice. Ken Bolin fits them to countries and the development of democracy. Whatever your unit is, mice.
It's an important unit. It's just a small one.
Is if we have cross-sectional data, we are fundamentally confounding within-person differences and between-person differences. So, do anxious people drink more is a between-person characteristic. If I'm more anxious than I usually am, do I drink more than I usually do is a within-person relation. And in cross-sectional data, that those are inextricably confounded. We can't pull them apart. Only can we distinguish those if we have a repeated measures like design. And so that's what we're going to talk about today, is how can we use repeated measures data. I'm going to dig up John Stuart Mill's corpse. Did you know we have John Stuart Mill's corpse?
Is he in your backyard too?
He is in my backyard. I have him in the back of my van, along with the chipmunk that I have a car where a chipmunk chewed into my air conditioning system and then died, and I never found him again. And so now John Stuart Mill is in my back as well. So Can I interject just briefly? I mean, I know like you're just
on a roll, but I just
no, please. You know what? Go ahead.
Wait, don't leave. Wait, you're supposed to do the. Okay. Well, anyway, things will be better this way. Trust me.
I'm still here.
See, this is why I should just keep quiet.
What? Make your point.
My point is, the repeated measures might be over a long period of time. So like a traditional longitudinal study where we're looking over a sort of a big part of the life course, like with mice, like a week, right? Or with people, it could be years. Or it could be over a short period of time. So it could also be like, are you throwing things at me? Are those creamers?
Go ahead.
Coffee? Sorry, I'm a little distracted. But it could also be over a short period of time. Behave yourself. So you could be doing something like a smoking cessation study and looking at number of cigarettes smoked per day as a function of some treatment. So it doesn't have to necessarily be over a long period of time, but we're trying to look at within-person change over time and individual differences in that. Patrick, I think you had a point about...
May I return?
Did something about John Stuart Mill,
So-
is it relevant? It's all right. Very little of what we do is.
There are many, many reasons why we want longitudinal data. A big one is trying to distinguish these levels of effect. Another one is we might be interested in looking at how a measurement of a construct unfolds over time. We may want to do a whole variety of things. But of course, the very first one is to infer causal processes. And so John Stuart Mill, who was, early philosopher of science, had 3 conditions for inferring cause. The cause has to precede the effect, right? That's just, unless you're a Star Trek fan and are going to go around the world super fast so you can go back in time and get a whale, is we have to have the cause precedes the effect. And then Mill's other conditions were the cause has to be demonstrably related to the effect, however you define that, statistically and however you might estimate that. And then the third one, and this is what makes our job so much fun, is there are no other plausible alternatives to account for the effect, all right? So the big thing that we're doing is we want to get temporal precedence in. So let's say we're interested in the development of aggressive behavior in kids over time. All right, and so we're going to make up stuff. We have real data in the class that is June 12th through June 16th in longitudinal SEM, but it's a real data example of repeated measures in kids on aggressive behavior, and it's going to be age 6, 7, 8, 9. I'm going to simplify it a bit, all right? So let's say that we have aggressive behavior at age 6, and it's a manifest variable. We can talk about expanding this. And we use that to predict aggressive behavior at age 7. All right, so this is a predictor, this is an outcome. This is a simple path model that we would have. It's a path analysis, a one predictor regression. All of these things are similar. All right, in form, maybe we have some covariates we're interested in. That's fine, we can incorporate that. But we get something we call a stability coefficient. So let's just call it beta hat. You know what, I'm going to call it beta hat 7.6 because we're regressing age 7 on age 6. This is sometimes called a residualized change model because maybe we have some predictor from our covariates where we want to say, well, what is the relation between, say we have a treatment group that they're in, the relation between treatment and control in aggressive behavior at age 7 above and beyond what we know about it at age 6. All right, it's 2 time point. So John Stuart Mill's corpse is happy. He's happy just because we dug him up and he just gets to get out a little bit, but he's also happy because we have temporal precedence. Well, does that allow us to now unambiguously infer causality? No, that's the minimal criteria that you have. All right, so this is a 2 time point. One of my heroes in the field is David Ragosa, and he once said in a paper that 2 time points are better than 1, but not much better. All right, and so what if we had aggression at age 8? All right, we can add that. What about age 9? I'm going to stop here because I'm out of whiteboard space. So now we have beta hat 8.7, we have beta hat 9.8. Now we're starting to build what's called an autoregressive model. 6 predicts 7, 7 to 8, 8 to 9. Maybe we are interested in the covariates to 7 above and beyond 6. What if we want 8 above and beyond 7? All right, starts getting away from you. But what if we're also interested in, say, peer rejection? All right, it's totally hypothetical, but say that you were a kid growing up in Colorado in the 1970s and you were somewhat aggressive and you were rejected by your peer groups. It's just a total...
And you had a really bad haircut.
really... and horn-rimmed glasses.
Really bad haircut.
All right, what if we have peer rejection at age 6? So this is the extent to which you're rejected from positive social groups. Well, rejection at age 7, rejection, you see the copy and paste that we can do, the rejection at 9 and 8 and 7. So now we have these stabilities. But look at what we can do. We can correlate these guys, but we can look at what are sometimes called cross lags. All right? So this is what's called an autoregressive cross lag model. Autoregressive is we have these stabilities, and the cross lag is we're saying, well, does peer rejection at age 6 predict aggressive behavior at age 7 above and beyond aggression at age 6? 7 to 8, 7, 8 to 9, 8, 8 to 9, 8, 8 to... Oh boy, this starts getting confusing. It's a path model. It's SEM. It's measured variable. We can test this. We get a chi-square. We get an RMSEA. John Stuart Mill's corpse is happy, right? I get him a glass of wine. He's a Cabernet kind of guy, and so I give him a glass of Cabernet. Hard for him to drink. He doesn't have a lower jaw, and so it just kind of spills down the front of him. But there's one minor problem with it. Tiny. I don't want to be the guy. Tiny problem. Is rarely, if ever, are theories predicting these kinds of relations. That peer rejection at age 7 uniquely predicts aggressive behavior at age 8, above and beyond aggressive behavior at age 7. What we might hypothesize is there's a continuous developmental trajectory of aggressive behavior. Think about it as height or weight over time in kids. There's a smooth curve of increasing height, and you might measure that every year, and you don't think that age 6 height is causing age 7 height and age 7 height causes age 8 height. You think that, well, those are just time-specific measurements around that trajectory. We have a trajectory of aggressive behavior. We have a trajectory of peer rejection. And we might be interested in what are the characteristics of these trajectories and how do they relate to one another over time. That's the core of a growth model. Your reading assignment for today is Hamaker, Hamaker, et al. In 2015 in Psych Methods. We'll put this in the show notes. Ellen Hamaker, Utrecht University. Really, really wonderful scientist. Did you know she is a professor of longitudinal data analysis? I kid you not.
That's a department?
It is an endowed professorship, a named professorship.
Why don't we have those kinds of things?
So, because we work for a state university.
We also don't work that hard.
So, we don't... Now we're both in t-shirts. I even gave up at this point.
I mean, what's the point?
So, here's where I'm going to do the throw to Bauer, which is this approach is elegant, it's powerful, it's well understood, it's widely applied, as long as it doesn't bother you that it usually doesn't test the hypotheses we're most interested in.
Yeah. So we're going to do as we often do when we co-author a manuscript, is we're going to start with Patrick's stuff, we're going to erase it all, and then I'm going to redo it. That's about right? Yeah.
You know, there's an entire bowl of creamers over there. I can,
enough,
I can do this all day long.
Oh boy. All right. So
those are pre-pandemic creamers too.
Ooh, they're dangerous now. So we're gonna work our way toward this idea of a developmental trajectory, right? So we had aggression at age 6, aggression at age 7, aggression at age 8, and we were kind of just looking at how one predicts the next, but we're gonna reconceptualize this a little bit, and we're gonna say, all right, we've got a time axis. Right, and we've observed people at 6, 7, 8, and 9, right? So we have age 6 and 7 and 8 and 9, and we're observing them across those time points. right? And let's start out by just assuming that we only measured them twice. We got kids at age 6 and we got kids again at age 9. And we want to look at how is aggression changing over time, right? So we pick one random participant from Colorado, PJ, and we look at PJ's aggression at age 6 and we get a data point, right? And then we look at PJ again 3 years later and PJ's aggression is now up here, right? And so we could say, oh, okay, well, I can see there's positive change there, right? I can connect the dots and I can say, look, there's the change score, right? That's just a raw score change. I can say, okay, looks like there's a positive change there. But I've got this longitudinal data, right? And if I've only got the 2 time points, I can't really separate the change that I'm observing from any kind of error or noise or any unreliability in measurement, right? So with the longitudinal data, what's pretty cool is I've also got measures of little PJ at age 7 and at age 8. And now I could connect the dots and I could say, well, there's positive change here and there's negative change there and there's positive change there, right? But instead, I'm going to rely on this idea that what I'm really observing here are just snapshots of an underlying trajectory. That poor little PJ, perhaps as a function of his really bad haircut and big collars on his shirt, and we have lots of photos.
We do.
And, you know, crippling pure rejection is becoming more and more, which hasn't stopped, is becoming more and more aggressive over time, right? And so
I thought you were my friend.
anyway, so you throw creamers at your friends. Anyway, so we've got this idea that little PJ is following some kind of trajectory. And these repeated measures that we're observing, right, they're not a perfect reflection of that trajectory, right? You know, PJ was a little more aggressive on this day than maybe would be typical for him as a 7-year-old and a little less maybe as a 6-year-old. There's going to be some scatter around the line because our measures aren't perfect and there are things that happen in the moment and there's unreliability and so forth. But we can use those repeated measures to infer the presence of this underlying trajectory, right? And the data points don't have to follow the line perfectly, right? There's going to be these little residuals around the line. So there's the allowance for the fact that the observed repeated measures are not a perfect reflection of the underlying trajectory, right? The trajectory itself is not directly observed, but we can infer its presence from the repeated measures over time. All right, so that's the trajectory for little PJ, right? But we don't really care about little PJ. I mean, we can pretend, but ultimately we don't really care about little PJ, right? Which is why he became more and more aggressive, right? But that's little PJ, right? And then here's, I don't know, we'll just say DB for lack of a better idea, right? And DB didn't suffer from peer rejection. DB was well liked by all of his peers and respected. And so,
well, it's because your teenage pictures look like you're out of a J. Crew catalog. We trade these embarrassing photos when we teach, and mine, oh my gosh, they look Photoshopped. They're so bad.
Yeah.
With horn rim glasses and salad bowl haircuts. And Dan looks like he's out of a fashion club. There's one, you're in a canoe and you're looking, it's an unfair fight.
And it's not just one picture.
It's
like for at least a decade, there's just like this progression of nerdiness.
Okay.
Anyway, all right, so each individual can have their own trajectory, right? And each individual is going to be described by a trajectory of change over time. Now, I happen to draw these as straight lines. They don't necessarily have to be straight lines. They could be curved, right? They could have various kinds of shapes. But we'll just start with the straight line because that's nice and easy, and we all suffered through geometry, so we understand intercepts and slopes of a line.
Most of us.
Most of us, right? So each of these lines is going to be characterized by some starting point, right? And some rate of change over time, right? So this is the starting point for this person, and then for PJ it's here, and for DB it's here. And so usually we're going to code our time axis as 0, 1, 2, 3. Right, so that our intercept will be interpretable at that first time point, right? Your intercept in a regression is always the expected value where the predictor is 0. So we're going to put time 0 there. That's going to put our intercepts right there, right? So we have sort of an initial status, initial level of aggressive behavior, and then we've got these rates of change over time, and they can be different across persons. And I'm going to use another color because that's so much better, isn't it?
Wow.
Isn't that like way better with the red?
Yeah.
Totally stands out.
Probably just stop here.
All right, so we have this collection of unobserved trajectories that we can infer on the basis of the observed repeated measures. And when we're inferring something unobserved on the basis of observed indicators, right, that takes us into a latent factor model, right? So we can view these trajectories as being represented by underlying latent factors. There's a latent intercept to capture starting point, and there's a latent slope to capture rate of change over time, right? And so with our latent curve model, we're going to represent the components of these underlying trajectories, their intercepts and slopes, in terms of latent factors that we can infer from the patterns of correlations and variance and covariance and means of our repeated measures, our observed data. And so that then is going to take us to our path diagram. You desperately want to add something here. You want to see the mean.
Effect.
You want to see the mean. I knew it.
It's right.
All right, so we've got this collection, right? We're going to represent these through latent factors, but Patrick really loves averages, right? So he wants to know what is the average trajectory, right? And it's going to be somewhere in there. Notice I used green. I'm really colorful today, right? We're going to have some average trajectory, and then there's going to be some variance around that, right? So there's some variance associated with the intercepts where people start, and then you could imagine we could take all these different slopes and we could look at their variance as well. So we have a mean trajectory that we're going to want to look at. We also have variances and covariances among these parameters. Are you happy now?
No, but it's sufficient.
All right, and then of
minimally.
course, remember we have the repeated measures scattered around the
Sorry.
trajectories, and so. All right, inhale
Okay.
deeply.
I know. You and I walk out of here kind of stumbling around him with 5 fewer IQ points than we walked in, which for you is not missed, but for me, like I was going to the plate with 2 strikes to begin with. So the key here,
What are you?
I tried to be cool and flip it, and then I dropped it.
Can you juggle?
I can't. You know what? Okay, ready?
Wow, with one hand.
It's like a $2,000 computer. I just pelted with it. Okay, dude, we're hemorrhaging time.
That was almost good.
That was almost good. That's going to be my memoir, is almost good.
I was about to compliment you. Thank goodness.
Well, I'm glad I clipped that, got that in the bud. All right, so the term latent it's just something that we believe to exist, but that we can't directly observe it. But using the statistical framework that we have available to us, we can use information that we did observe to make probabilistic inferences about what we did not observe. So the irony is we often call this a whiteboard problem. A whiteboard problem.
So cool.
Why? Because I'm going to draw in the same rectangles for the same measures on the same kids of aggressive behavior as we did for the ARCL model that we looked at. All right, aggressives age 6, 7, 8, and 9. All right. And Hancock and I have a paper, I'll put it in the show notes, but we literally talk about the whiteboard problem, and we go into details about this, especially when we have a second construct.
I thought we agreed not to talk about Hancock.
No, you agree.
You know I get sensitive.
You get sensitive. But you established 5 minutes ago you're not my friend, so,
I really don't care.
I don't. Okay, notice we had 6 predicting 7, 7 predicting 8, 8 predicting 9. Well, the whiteboard problem is we say, that's not the model I believe gave rise to the data that I observed. I don't think that age 6 in part caused age 7, and that age 7 in part caused age 8. What I think is these are samplings of the behavior around the smoothed trajectory. So what we're going to do is we're going to estimate this as a confirmatory factor analysis model. All right? So we're going to have a latent factor, and I'm going to call it alpha for intercept. All right? And I'm going to have this predict each of the items with a loading fixed to 1.0. It's not a regular CFA where we estimate these. We're fixing those to 1. Well, what is this doing? This is setting up the level, the overall level of the individual in the mean, and where that is at the beginning, is it at the middle, is it at the end of the repeated measures, depends upon how we code the next factor that we're going to put in. But each latent variable is going to have a variance, and I'm going to call this psi alpha, and it's going to have a mean. All right, and I'm going to call this mu alpha. These aren't traditional literal terms, but they're what I like, and I'm doing on the fly. All right, what does this model imply? Well, the mean, we're going to have time here and aggression here, and the mean, which is constant over time, is just going to be some overall flat level. And the variance is how variable are individuals in that flat level. All right, so all it means is not growing over time. Some people are higher, some people are lower, so we have a mean, and we have individual variability in that mean. All right, so we have these trajectories, but we believe them to be horizontal. Well, maybe they are, right? Maybe we have daily measures of stress and they're not systematically increasing or decreasing. But what if we have what Dan showed, right? Where we have PJ's aggressive behavior and Danny Boy's aggressive behavior. Well, it's just an SEM. We can do anything we want. I can add a second factor that I'm going to boldly call beta. This is going to have a variance. I'll call it psi beta beta. It's going to have a mean, all right? And I'm going to call that mu beta. And what's pretty cool is it's going to covary with alpha. And now we can do a whole number of things with this. But what I'm going to do is I'm going to dash this line because that's 0, it's not really there. But here's 1 and 2 and 3. Now remember Dan, excuse me, had the plot where we had 0, 1, 2, and 3. Well, there's 0, 1, 2, and 3. We're putting time in the factor loading matrix. This is aggression. And now we are going to have a mean trajectory for all individuals. Well, what is that intercept? That's mu alpha. What is that slope? That's mu beta, right? So there's mu alpha and there's mu beta. We have a mean intercept and a mean slope. But we have individual trajectories all around this, right? 200 kids, we have 200 trajectories. Well, there's a variance of those intercepts. Wait for it. It's right there, the variance of the intercept. It's harder to draw the variance of the slopes. I'm just going to kind of do this. Some people are steeper, some people are less steep. They vary around that mean. Well, wait for it. There it is. It's in the variance of that factor. So our theory says we believe these individual continuous trajectories exist and they're governed by some mean variance some mean structure and some variance covariance structure. And then we're going to use the data that we have to obtain point estimates of the starting point and the rate of change. And as Dan said, we're making it easy with a line. Yeah, who cares? We can make it a curve, we can have a piecewise, we can do all sorts of really cool things that, notice we have 1 minute. We're going to go long because you get exactly what you pay for. Plus, you were throwing creamers at me, which was completely unprofessional.
It was inappropriate. It really was.
This is sometimes called an unconditional model. Do you want me to spray it?
No, I'll take care of it.
Boy,
I want my own.
Okay,
fumes.
yeah, boy. But it's called an unconditional model, and the reason is that we're defining latent variables to get these components of the underlying trajectory, but we haven't done anything with them yet. Yeah. Remember, we had covariates, we had things, well...
Right. So, before I jump into the next thing, I just want to say that one other parameter here that Patrick failed to mention.
For time, but go ahead.
That's the covariance between the intercept and slope. How is initial status related to rate of change over time? And in his diagram, whether he intended to or not, you can see steeper slopes tend to go with higher intercepts. That's over there. Wait for it, right? That's it. Anyway.
Well, It's a very dynamic-like parameter. Does where you start relate to where you go over time? And if you're out in the education field, which I think is just fascinating on a lot of different levels, this is the whole motivation for Head Start, is to bring kids up to normative levels of reading and writing to enter kindergarten, because if they're lower when they enter school, they do not increase as steeply, and we're able to obtain an estimate of that.
I'm just going to erase that too.
Really? Because I kind of liked it.
Well, sorry. I've got the whiteboard.
I can't even read my own handwriting.
Yeah. All right, so what we're going to do next, we're going to say, remember all that variability that I just erased? Right? We've observed it in this unconditional latent curve model, but we haven't yet predicted it, right? And we might want to know, why is it that some kids, like poor little PJ, start with higher antisocial behavior, higher aggression, and show greater increases over time, whereas other kids are well-liked, right? And just go. Anyway, all right, so we can add a predictor to our model, right? Could be any predictor, but we'll just say maybe it's pure rejection, right, at age 6, right? And so that's going to predict that intercept and that slope, right? And so now we have residual values around the intercept, residual values around the slope, and they're going to have some variance and covariance. But the main point is that we are now predicting what that intercept looks like and what that slope looks like, right? So we're going to get coefficient estimates, gammas. I'm just going to call it gamma alpha and gamma beta, because we're just making up notation as we go along, right? And they're going to tell us, for a 1 unit change in x, what does that predict for the intercept? There's going to be a gamma alpha unit change in that intercept. And for a 1 unit change in pure rejection, we're going to see a gamma beta unit change in the rate of increase in antisocial behavior. So a predictor like this that's measured once or stable over time is referred to as a time-invariant covariate, or TIC. And that's typically how that's going to enter the model, is it's going to predict the growth factors directly. And we want to know, why do some people show one trajectory and other people show a different trajectory? How much of the variance in alpha and beta can we explain on the basis of a predictor? And of course, we can have more than one of them. We don't have to have just one X. So that's a time-invariant covariate, but the other kind of predictor we can have is a time-varying covariate. So this is something that is itself varying over time, and if Patrick had drawn the diagram a little lower, I would have space to put it in here, but you can kind of imagine we could have an X at age 6 predicting here.
Well, I was tall enough myself.
At 7. Oh, yeah, the height jokes, I love those. And, we could measure something. So this could be pure rejection at each time point, predicting the aggression level at that same time point, right? And so we could also have those kinds of time-varying covariates in the model, except that it's a little odd because we've got repeated measures for aggression that we have this beautiful growth model for, but we don't have any, and it's not just because I ran out of whiteboard and I don't want to draw on the wall, we don't have any kind of growth process for the time-varying covariate, right? And so that's something that we might want to think about building in as well.
And so with that, to make one point, if you don't mind me jumping back briefly, is this X introduces, remember I said there was, the model without X was unconditional. There's just one trajectory. There's a starting point and a rate of change, and there's variability around this. Well, what this is allowing is we get a model implied trajectory as a function of your value on the predictor. So let's say that you were at high or medium or low values of pure rejection, that you might have a different model implied trajectory as a function of X that is transmitted through these gammas. And so you get into the wonderful part of our field, which we talked about actually on the first couple of episodes, which is it depends, right? What is the trajectory of aggressive behavior? Well, if it is an unconditional model, it starts at 1.6 and increases 0.8 units per year. It's really pathetic because that's actually the point estimate.
That's the actual point estimate.
From our, we really need to get out more. But if you say bring in treatment condition as a predictor, say you're trying to do an intervention to reduce aggressive behavior, well, then you say, well, what is the trajectory of aggressive behavior? You say, well, it depends. Is it for kids in the control group or kids in the treatment group? Because they have different trajectories. And so it's really fascinating what you can do. But we're going to go back and see how easily I can reach the top of the board.
It's great how the physical therapy is.
I know it is, it is. I'm going to just say aggression at 6, at 7, at 8, and at 9. And remember, we had peer rejection. And so what we're going to have is just peer rejection at 6, at peer rejection at 7. I can't talk and write. I can't even write and write. Peer rejection at 8, peer rejection at 9. All right? And this is, again, in collaboration with He Who Shall Not Be Named, this is what we really focused on, is what we referred to as co-development. But what Dan showed was, oh, look, we can build this growth model for aggressive behavior, and then we can have peer rejection predict the time, but that's not fair, right? Each of us have multiple kids, and we've heard once or twice, that's not fair. Okay, so you shrug and say, fine, quit whining, and we'll build a growth model for aggressive behavior, right? So we got a little residual. Pardon me?
For peer rejection.
Well, no. We build a growth model for aggressive behavior. We build a growth model for peer rejection, and then looky. We can correlate, just like a CFA. I appreciate my path diagram is not as helpful as it might otherwise be. But notice we have an alpha and beta for aggressive behavior, and we have an alpha and beta for peer rejection. This is sometimes called a bivariate growth model. We have individual variability in starting point and rate of change for aggression, individual variability in starting point and rate of change for peer rejection. And we can say, how do those parameters relate to one another? We can have our TICs here, where we have X1 and X2 and X3, and they can relate to the growth factors in any way we want. They can saturate and predict them all. We can predict a handful of them. In principle, we could have a TVC, say that we had, a measure of in that year was the child's parents divorced or not. We could still have like a divorce TVC that predicts each of those in the present. Is when you really embrace that whiteboard aspect, we can build any model that we want that now, keep in mind, these are the same squares that we had in the autoregressive, but now with the same measures and the same samples, we are vastly better able to match our statistical model to our theoretical model that gave rise to our research hypotheses.
It looks like a spider to me.
It's like, yeah, that's super clear. And then we can do this, and there's a new package in R that allows us to estimate from here over, I know, that's my bad arm actually, and all of that can predict Z.
Yeah, the last bullet point was where do we go from here? And I think we wrap it up.
The door? Do we go here? This is our entire outline. And where do we go from here? And I think it's to mute.
I think, yeah. Yeah, so why don't we just mention briefly, there are lots of directions we could take this, but we are clearly not going to have time. We could do nonlinear growth. Yep. We could do multiple group modeling. We could do, I don't know.
We could have latent measures of exogenous variables.
Second order growth models.
And then there are a whole class, and maybe we could do a session on this at one point. They're called hybrid models, and they try to bring together the bivariate growth with the autoregressive-like structure. Because notice,
this is super helpful.
This is
at this point.
Maybe of limited utility. But what's very odd is when we focus on the trajectories, that actually becomes a between-person characteristic. And what I mean is I am from Colorado, I am 57 years old, my intercept is 1.5, and my slope is 0.3. John Stuart Mill's corpse is like grunting over in the corner because where's temporal precedence? We don't have temporal precedence anymore. And although we have concerns about the autoregressive, we've lost earlier peer rejection predicting later aggressive and earlier aggressive predicting later peer rejection. And there's been a whole flurry of work in the area to kind of try to take the best of both worlds and have trajectories and time lags, but that's for a whole nother conversation.
And one other extension that I really like is when we look at models where repeated measures are not necessarily continuous. They could be ordinal, they could be binary, and we can still infer underlying growth, continuous trajectories from those binary or ordinal data.
And if you are foolish enough to hang out with us more, we really do have a 5-day class on this, longitudinal SEM, and we pick at every aspect, show you how to do it, have real data, all of that. There's that. Now, I will finish with, if you don't mind, of discuss where to go from there, which is a super helpful bullet, is...
It's a nice outline.
It is a nice outline. Notice that we're using a manifest variable. That is, we have a set of items, we add them up, we take a mean. And we talked about in episode 1 with the SEM that there's a real limitation to doing that often, which is we're making very stringent assumptions about the measurement structure, about equal contribution of each item to the composite, about unreliability, perfect measurement. And where we really want to go is to say, well, can we do some kind of multiple indicator latent factor? And so what we thought is for next week, if you will come and join us again, is we're going to talk about 30 or 40 minutes of what is factor analysis? What is exploratory factor analysis? What is confirmatory factor analysis? We're not going to tie it directly to this, but we'll talk about, you know, how might we be able to do better than a mean score or a sum score in the kind of work that we do.
Which answers one of the questions in the chat.
Was there
How
a
do
question?
You do this with multiple indicator latent factors?
Boy, all right. The man who shall not be named has a paper on second order growth models, and I'll put that in the show notes.
Edit it out later, but yeah.
Oh, you don't, yeah. You, in principle, can
That's
do kind
so
of this.
unhelpful.
Is fine. Do that. I don't care. Go nuts. We have the full SEM. Absolutely. You can make these a multiple indicator latent factor. It's called a second order growth model because you have multiple indicators that themselves are then loading on these growth factors. The problem is what all of you have to deal with in your own personal relationships of whatever form those take, which is pick your battles, right? Is we often can't do everything that we want to do within the confines of a model because of complexity, because of sample size, because of instability of model estimation. And so people have waxed poetic about these multiple indicator latent factors, but if you have 6 or 8 repeated measures, 2 constructs, 10 items per measure, you have hundreds of parameters to estimate, and you might have a sample of 180. And the pick your battle is, we want an Audi A8. That's my car I want at some point. I want an Audi A8. We can afford an 18-year-old Toyota Corolla, which is the car I drive. So
Chipmunk free.
You chipmunk free. So that is the answer. And there's lots of interesting work going on about, can you estimate a multiple indicator latent factor and get a factor score that you then take to a growth model? There are lots of interesting things.
The really cool aspect of this, at least in my opinion, and I don't know why I'm pointing at this because it really communicates next to nothing.
No, this predicts Z.
It's beautiful.
It predicts Z.
It predicts Z. We've got this multiple indicator latent factor at age 6, age 7, age 8, age 9. I feel like I have to verbally say it because the diagram's not helpful. We can test whether or not the measurement model stays the same over time, right? It's a little bit embarrassing to talk about change in a construct if you haven't established that the measurement of that construct is not itself changing and recalibrating over time. So If you have the ability, if you have a large enough sample size where you can jacket the complexity, it does provide you with some really nice opportunities to evaluate the measurement of your constructs over time.
And to square the circle where we began is, I alluded to that, is there are many reasons why we might like longitudinal data, temporal precedence, disaggregating within and between effects. But a big one that is not often capitalized is making as a substantive theoretical question, how does the measurement unfold over time? Even if you never get to growth. Dan and I have worked with colleagues in looking at anxiety and depression in 5-year-olds, 10-year-olds, and 15-year-olds. I don't know how many of you have kids, but Dan and I both have kids who have transited through teens. Is anxiety at age 5, 10, and 15 is expressed fundamentally differently as a function of age, even though you believe there's a single latent construct, right? That is sometimes called heterotypic continuity. See, I know stuff about psychology.
You know terms from
psychology. I know it rhymes,
right?
heterotypic continuity. I saw them open for Van Halen in the mid-'80s. But heterotypic continuity is what it sounds like. Heterotypic is the indicators, the expression, the observed data that you have may change over time, but there's continuity in the underlying structure. And so there are really interesting theoretical questions that are just longitudinal factor analysis that examine these kinds of things.
All right, so I'm going to throw you another one.
All right.
Or maybe I'll start and you can then restate
it. Use half our time just setting up what you're going to do.
Okay, so there was a question. Just going to whack you, man. There was a question about the relative advantages of using a multiple group latent curve model versus including a grouping variable as a time-invariant covariate in a conditional latent curve model. And I'll give the quick answer and then Patrick will expand on it for 10 minutes.
No, I won't expand on it. I'll repeat what you said and then claim it as my own.
So like all the
No, that's our papers, our everything.
Excellent.
Yep.
So the conditional latent curve model is basically going to give you mean differences across groups. So does the mean of the intercept factor vary between, let's say, the treatment group and the control group? Does the mean of the slope factor vary between the treatment group and the control group? So you get differences in the conditional means of the growth factors from a traditional TIC model. The multiple group model allows any parameter to differ across the groups. So not only might the means of the growth factors differ across groups, but the variances of the growth factors could also differ. So in the data set that we look at in the workshop that's kind of related to this example, we see that there's much greater variance in antisocial behavior trajectories for boys than there is for girls. Well, you wouldn't see that in a standard conditional latent curve model because you're only getting at mean differences. The multiple group model allows you to see those differences in heterogeneity as well. So that's the main advantage of the multiple group model, is you have access to more parameters that could differ across groups, in particular variance and covariance parameters. The downside, of course, is the complexity issue, is you're estimating more parameters, you're sort of, not exactly, but kind of splitting your sample up a little bit, and so your sample sizes are going to have to be larger to get adequate power and precision on those additional parameter estimates. Okay, would you like to?
I uncharacteristically have nothing to add. Yep.
All righty.
And I was just going to add something, I was going to make a point, but like literally you said that. I'm going to do it anyway. In the single group model, there's one variance. In the multiple group, we allow it to differ. And, and I reiterate, I don't repeat, but I reiterate, is you can only buy the car that you can afford. And there are times where you want to make that testable, but the characteristics of your sample don't allow it. And, that's just life in the big city, and that's the pick your battles.
Yeah.
Now, there are other things that you can do. You can look at distributions, you can look at plots, you can kind of see if something fundamentally different is going on. I personally love the multiple group framework because a single group is forcing you to have equal parameters, right? You and I decided is like all of life is we're just petulant teenagers, right? Is you can't make me empty the dishwasher, kind of thing. Is the single group makes those variances and covariances be equal, and the multiple group allows you the opportunity to set them be equal if that's consistent with the data, but the opportunity to allow them to be different. So I think there are real advantages to that.
All right, last one, I think. Compare and contrast the multi-level growth model to what we've seen here.
That's
similarities and differences.
Similarities and differences. I think we should do a whole episode on that. And so I'm not going to answer it. Very briefly, I'm talking very briefly, now you threw me, for a broad class of models, the MLM and the SEM are numerically identical. They're not kind of similar, you wouldn't write the same discussion. They are, I saw them open for gin blossoms, the numerically isomorphics. They were great. But they're numerically isomorphic. What does that mean? Is they're numerically indistinguishable. They're not kind of the same, they're exactly the same. And the SEM is motivated by having fallible indicators used to define underlying latent factors. The multi-level model is motivated by having repeated measures nested within individuals and estimating fixed effects and random effects. Multi-level fixed effects are latent variable means. Multi-level random effects are latent variable variances. They're exactly the same. All right, where do they kind of separate? I love the multi-level model, and we won't get into all the details. Multi-level model is super well suited for 3-level data. You have time within kid, kid within classroom. All right, you have a 3-level model. It's super well situated to do what are called high-density data. Instead of 5 or 6 or 7 repeated measures, we might have 20, right? Intensive longitudinal data. SEM really starts to struggle with that. The MLM doesn't. Where does the SEM kind of go its own way? Multiple indicator latent factors that we can do measurement models, and we have much more flexibility.
As you can see,
multivariate models. There are ways of doing multivariate models in MLM, but it's a heavy lift and you trick it and you still hit a wall. And I think the SEM is very, very well suited. So that's...
And the MLM does not give you tests of fit, whereas the SEM will. So if you don't want to know that your model doesn't fit, use the MLM. If you want to have a testable model, use the SEM. Right? So if you get bad fit in the SEM, just switch over.
Okay, I'm going to edit that out. Oh, wait, this is live.
I thought we were doing professional development.
You can't edit out live. Okay, we got to go. Hey, everybody, thank you so much for your time. Thanks for hanging out with us. In a week, we got our dates mixed up. Are we on Thursday next time? Okay, next Thursday, we're going to do EFA, CFA. And as a teaser, the exploratory factor analysis isn't really exploratory, and the confirmatory factor analysis isn't really confirmatory. But other than that, take care, everybody. Bye-bye.